Greetings, everyone. This is Mr. Mall, and in this podcast, we're going to talk about the terminal voltage of real batteries. And shown is the related homework that you could do to go along with this podcast. Okay, so we're going to talk about real batteries, batteries that aren't behaving ideally, and it turns out that real life batteries are not able to provide the full ideal voltage. Real-life batteries cannot provide the full ideal voltage. Okay, so that full ideal voltage, the symbols we're going to use for that is EMF. Full ideal voltage. What is the EMF? Okay, EMF is, I'll draw a little arrow over here. EMF is known as the electromotive force. And basically what that term is talking about is the overall charge pushing ability of my battery. Overall charge pushing ability. So what this is saying is that real life batteries are not able to provide this entire full ideal voltage EMF, because of internal resistance within the battery. Okay, so I'm going to go ahead and draw some pictures here. We're going to talk about some circuits that I'm going to be drawing. So I'm going to look at a battery, and I'm going to go ahead and draw my battery here. Okay, so here's the end of my battery here. Here's my little nub. Okay, so I'm going to call this point B. I'm going to call this point on my circuit A. Okay, so I'm going to go ahead and draw. And let's say this battery is hooked to a single resistor. And I'm going to call that known resistance in the resistor R. Okay, so I'm trying to push current through this thing, and it turns out that inside the battery some stuff is happening. And I look at the battery, and let's say it's a 9-volt battery. I'm assuming that it's going to be providing 9 volts. Okay, but that's not the actual true voltage of the battery. So I would have in here some number of volts, my ideal electromotive force, ideal EMF. And the symbol for this ideal EMF, and I'll just put my little symbol epsilon here, like a little curvy E. Okay, so there it is. And it says the reason why we can't get that full ideal EMF is because there's some internal resistance within the battery that's going to also be resisting flow. So I'm going to call that internal resistance a lowercase r. Okay, so the equation I'm about to describe for you is not on our equation sheet, but the basic idea you need to be able to recall. Okay, so I'm going to describe this circuit right here, and this little circuit with one resistor is a circuit that behaves like, say, circuit shown behaves like a perfect battery providing the ideal EMF with two resistors in series. Okay, we've got one that's kind of internal, one resistor we're treating as like a little internal resistor, and there's that one external resistor. Okay, so it adds a little bit of resistance. So to find the terminal voltage, which is going to be this term here, VAB, where A and B are the 2 points on either side of a battery. To find that terminal voltage, we can take the ideal EMF and subtract basically the potential difference at that little resistor. How much energy per charge is lost. So remembering that V is equal to I times R, I can take the current and I can take that little value of my resistance and I can subtract that potential difference loss. And this is my internal resistance. Okay. So remember, this here was just that voltage drop due to the internal resistance. Okay. So we're gonna use this little equation here to help us solve some problems where batteries are not behaving ideally, and we've got to worry about any internal resistance that the battery has opposing flow. Okay, so we're going to do 2 example problems, taking this principle and applying it to some situations. The first question says calculate the terminal voltage for a battery with an EMF of 9 volts and an internal resistance of 0.5 ohms. And this is going to be an exact same picture on the previous slide. Pick on last slide is something that has a battery hooked up to a single resistor. Okay, a real battery hooked up to a single resistor. So we hook it up to a 100 ohm resistor, and we know its internal resistance. So the first question says find the terminal voltage. So to find the terminal voltage, I need to take that ideal voltage the battery can provide, that ideal electromotive force, and subtract the voltage drop due to the internal resistance, I times lowercase r. Okay, so I'm going to find that internal resistance, and I know that the ideal voltage for this is the 9 volts minus I times r. Okay, problem, I don't have the current, but I do have Ohm's law, and I know that in this overall circuit, I know actually all the resistance that's going on, okay, all the different things that are providing resistance. So if I want to look at the circuit as 2 little resistors in series, I can find the total current by looking at the total voltage being applied across the entire circuit and the total resistance being applied across the entire circuit. Okay. Remember that V total, what we're really talking about is that ideal EMF at this point. Okay, so I can calculate that total current by taking my 9 volts and dividing by the total resistance. Well, I can treat my resistor and the internal resistance as being 2 resistors in series, so I'm just going to add them together. They're in series, so I can add them together. That's how we add resistors in series. So 100.5 ohms, and I'm going to get a final current of 0.0896 amps. So this is the current flowing due to the resistance of both the battery and the resistor in there. Okay, so once I know my current, now I can go back in and plug in for my current 0.0896 amps times my internal resistance of 0.5 ohms, and I'm going to get that my terminal voltage, what the battery is actually able to provide, is 8.96 volts. Okay, 8.96 volts. And now that I know what the terminal voltage with the battery was, I'm going to go back and kind of show you that if I look at, because I know that voltage now, I can go back and look and say, okay, well that's the voltage that resistor feels. If we had to go back and say, well, what was the current through my 100 ohm resistor? I'm just showing you kind of another thing that we could do with this information is if I wanted to know the current flowing through just my 100 ohm resistor, I could take the voltage at that resistor, but I can't use the 9 volts in this problem. I would have to use the actual terminal voltage, which is the actual voltage that the battery can provide. Okay, so I would need to know that current, and then I could use the resistance of that there. And what I'm going to find, of course, is that for this is a series circuit, we're going to get the exact same answer as the current flowing through the entire circuit, because everything is in series, and that current is going to be the same throughout the circuit. Okay, so just kind of pointing out, if you're asked to use the current at some point, if there's a real battery involved, you would actually need to know what that ideal voltage was. In this case, we already knew the current in the entire circuit, but this is just kind of a confirmation. All right, the last thing I want to do is example number 11. Example number 11 says a certain battery has an EMF of 9 volts, but its terminal voltage drops down to 8.6 volts when it's connected across a resistor that's drawing 2.6 amps of current. So I've got a battery, again, it has 9 volts of, it has an EMF of 9 volts, and it's hooked up to a single resistor. I'm just drawing a little picture. And so, I can think of this, again, as being, something that has an internal resistance in there. Okay, what is the internal resistance of the battery? Well, they give me the terminal resistance, the terminal voltage, and I know that that's going to be equal to the ideal voltage, or the EMF, minus the voltage drop due to the internal resistance, or IR. So I actually know my terminal voltage is 8.6, and I'm trying to solve for the internal resistance of the battery. It's a 9 volt battery, so it should be giving me 9 volts of potential difference overall. And then I can subtract my current, which they actually gave me, 2.6 amps actually are getting pushed through, times R. Okay? And when I solve for R, I'm going to get that the resistance is equal to 0.154 ohms. I'm just solving for a different thing. Okay. The last part of the problem says, what is the resistance of the resistor that the battery is connected to? So we found out all about this internal resistance, but now I want to know what is that resistor that the battery is connected to. Okay, so a couple different ways I could look at this. I want to find the resistance of that specific battery. So I could look at, if I wanted to find the resistance, I could use Ohm's law to talk about what's going on at that resistor. So I could look at the current flowing through that resistor, and it's related to the voltage at the resistor, but the resistor only feels the terminal voltage. It doesn't feel the ideal EMF. So I've got to use that expression. So when I solve for R, okay, I can cross multiply, get R by itself. R is going to be equal to VAB divided by I sub R. Okay. I can solve, and I can get my absolute, my terminal voltage was 8.6 divided by I times R. And so I know my current, I know my R, that's going to be equal to, I of the resistor, not IR. This is just I of the resistor, not I times R. So I have the current flowing through the resistor, So it's all in series, so that's 2.6 amps. And then I'm going to get my resistance is equal to 3.31 ohms. So I can find the resistance of the resistor kind of using and looking from the resistor's point of view. I could actually also find that resistance of the resistor from kind of looking at the current as the entire circuit as kind of like the two little resistors in series. So if I'm looking at the current using Ohm's law, I know that the total voltage of the entire circuit, and that's really talking about, in this case, I'm going to use the electromotive force. The total voltage applied is equal to the R total. That's true. And in this case, the total voltage is the is the electromotive force, and the R total is just going to be, we've got resistors in series. Okay, so we're just going to sum up the individual resistors. So I've got R plus 0.154, and I could take 9 divided by that, and if I set that equal to 2.6, I can solve for R. Again, I've got to cross multiply, and when I get R by itself, do a little bit of algebra, we're going to get the R is equal to, again, 3.31 ohms. Okay, so an alternate way to solve for the problem. All right, this has been a short podcast on terminal voltage of real batteries, and I hope that it's been helpful.